Hello everyone, we are at the topic of MOSFETs and we're going to look at CMOS circuits and CMOS technology today. So CMOS or complementary MOS technology uses both NMOS and PMOS transistors. Nowadays CMOS is the most widely used for the IC technologies for both analog and digital circuits. The picture shows an implementation of a building block of CMOS technology that consists of an NMOS and PMOS built on a P-type body. So let's take a look at how we can use this technology to build an inverter circuit that's most widely used in digital circuits. Okay. Previously we saw an inverter circuit using an NMOS transistor, as you can see in this picture, and we saw the transfer function of this circuit, VI versus Vout, and we saw that it operates as an inverter for VI less than threshold voltage. Vout is equal to VDD, and for VI large value equal to VDD, Vout is a small value but non-zero. So the idea for CMOS inverter is to replace this resistor at the drain or RD with a PMOS transistor, and this will give us the CMOS inverter. So the benefits of doing so is that you're going to have a low state of 0 volts and a high state of VDD. So Vout changes between 0 volt as the low value and VDD as the high value. So that's going to give you the maximum signal swing, because the range of change for Vout is maximum, and it is between 0 and power supply voltage. The other benefit is that when the output is at one of the stable states of low or high, the power dissipation is 0, meaning that ID in either one of these cases is equal to 0. We're going to see both of these benefits and study them next. Okay, so first let's take a look at one of the important cases of operation of MOSFETs, and when that's the case of ID equal to 0. So when MOSFET is in cutoff, we know that ID is equal to 0. However, ID of 0 doesn't necessarily mean that MOSFET is in cutoff region. To see that, let's assume that MOSFET is in triode region. I know that when MOSFET is on and it's in triode, that means V over drive is greater than 0, and drain to source voltage is less than V over drive voltage. I know the equation for the MOSFET operating in the triode region, the ID equation. This is the ID equation, and ID equal to 0 is going to result in VDS of equal to 0, because V over drive is greater than 0 and VDS is less than V over drive. So that this equation is going to result in VDS equal to 0. So let's check the case of ID being equal to 0 and transistor operating in the saturation region. So in the saturation region, because MOSFET is on, V over drive is greater than 0. Also, VDS is greater than V over drive. So I'm going to use the ID equation for the case of saturation and equate it with 0. That's going to give me V over drive equal to 0, but it's not valid because the transistor is on. When by the assumption of transistor operating in saturation region, I know that V over drive is greater than 0. So it's not possible for the transistor to operate in the saturation region and have an ID of equal to 0. So the only possibility of having transistor being on and ID is equal to 0 is when the transistor operates in the triode mode and VDS is equal to 0. In other words, if a MOSFET is on and ID is equal to 0, then we know that MOSFET operates in the triode mode and drain to source voltage is equal to 0. This is valid for both PMOS and NMOS transistors. So if you're dealing with a PMOS transistor, it can be on and ID of that transistor would be 0, providing that transistor operates in the triode mode and voltage of drain to source is equal to 0. We're going to use this case for studying or analyzing the CMOS-based inverter circuits. Okay, so here is this is our CMOS inverter circuit, as you can see here, and First, let's study the circuit equations. Gate to source KBL for transistor 1. This is my V gate to source of transistor 1. From this KBL, I know that VI is equal to VGS1, and for transistor 2 gate to source KBL, which is this path, is going to tell me that VDD equals to VSG, this is plus minus VSG2 plus VI. So I have another KBL from the loop that has drain to source of transistor 1 and source to drain of Q2. So let's label this one. This is plus minus VSD of transistor 2, and this is plus minus drain to source of transistor 1. So VDD, from this loop, I can say that VDD equals to VSD2 plus VDS1. Also, from this KCL at this node, I know that I drain 1 equals to I drain of transistor 2. And this small KVL in here is going to tell me that V out is equal to VDS1, and that is from this KVL. V out equals to VDD minus voltage of source to drain for transistor 2. Okay, now that we have these equations, let's take a look at studying two cases when VI is at high or VDD and when VI is equal to 0 volt, and that's a low state for input signal. Okay, first, when VI is equal to 0. When VI is equal to 0 for the gate to source transistor of transistor 1, I have VGS1 equals to VI, that's equal to 0, so it's less than threshold voltage for transistor 1. As a result, Q1 is off and I drain for transistor 1 is equal to 0. From the KCL, I know that ID1 equals to ID2 and that both of them are equal to 0. Let's check the state of transistor 2 next. So I'm going to label this one voltage of source to gate for transistor 2, and from the KVL in this loop I have VDD equals to voltage of source to gate up for transistor 2 plus VI. VI is equal to 0, as a result VSG2 is equal to VDD, and that is greater than threshold voltage for the p-type transistor. So Q2 is on. PMOS transistor is on and drain current of that transistor is equal to 0. This is the same case that we just saw, that it means a Q2 is in triad mode and voltage of source to drain for Q2 is equal to 0. I also know that V out is equal to VDD minus voltage of source to drain for transistor 2. VSD is equal to 0. As a result, V out is equal to VDD. So in summary, for VI equal to 0, output is at VDD, while ID1 and ID2 both are equal to 0. So you have 0 power dissipation when the output is at this state. Also, will remain in this state as long as input voltage is less than V threshold for NMOS transistor, as long as Q1 is at off state. Okay, so let's study the case of VI being high or VDD. So for transistor 2, I have voltage of SG2 equal to VDD minus VI. VI is VDD, so VSG2 equals to 0. This is less than a threshold voltage for Q2. As a result, Q2 is off, and I know that ID2 is equal to 0. From the KCL, again, I know that ID1 and ID2 are equal, and they're equal to 0. Voltage of gate to source 1, this VGS1 equals to VI, which is equal to VDD. It's greater than voltage of threshold for NMOS transistor. As a result, Q1 is on. Now I have the same case. Q1 is on, ID is equal to 0. I know that Q1 is in the triad mode, and voltage of drain to source for transistor 1 is equal to 0. That is the same as V out. V out equals to drain to source of transistor 1, and that's equal to 0. So when Vi is high, or at VDD, V out is equal to 0, and again at this state ID1 and ID2 both are equal to 0, and you have 0 power dissipation for this state. And gate will remain in this state as long as Vi is greater than VDD minus VTP, so that transistor 2, this Q2, is off. So here is this was the CMOS inverter analysis, circuit analysis. We showed that the output changes from 0 to VDD, that has the maximum output swing, that we have the maximum output signal swing, and there is 0 power dissipation when the output is at one of the stable states of low or high.